Hi and welcome back to the shack. So last week we had a look at the input filter and how to filter noise on our supply from getting into our circuits. This week we're going to look at how to take that incoming 12 volt supply and step it down to the 5 volts we need in an RF quiet way. So if we're taking a higher input voltage and reducing it to a lower voltage, this is called stepping down, and there are two ways to do it. One of which is an LDO and the other one is a switching regulator. And we're going to cover these in turn, starting with the LDO box here, and we have V in, and we have V out, and we have some voltage here, let's say 12 volts, and some output voltage, let's say we want to regulate it to 5 volts. And the way these look like internally, imagine there is some current flowing through here, we've got some load, is these look like a variable resistor internally. And what these are doing is there's a controller in here, and what this is doing is this is adjusting the value of this resistor to ensure that for whatever current is coming out here, that we always get 5 volts out. So the input current here is equal to the output current, and the voltage dropped through here is going to be, I times R, where R is this sort of magical variable resistor. And because we have an input and we want the output to be 12, the controller will just adjust this R. However, this has a couple of downsides, one of which is power dissipation. So because this is a resistor, it's going to be dissipating power, and it's going to be dissipating power is the current flowing through it multiplied by the voltage across it. So you can see that the power this is going to dissipate is going to increase if this is bigger or this is smaller, so the difference between the two gets greater, and if the current flowing through it increases. However, these do have some nice properties. One of the nice ones is they tend to attenuate noise that goes through, so any sort of AC that's present on here will be generally attenuated by this device by the time it gets to here. As an example of something that uses an LDO, here is my Anglian transverter, and it's an excellent 2-meter transverter, and the LDO is up here in the corner, it's probably the largest part on the actual board. And this thing takes 12 volts in and is regulating it down to, I believe, 5. But if we go, we've got 7 volts dropped across it, because 12 minus 5, and we've got 1/4 of an amp in it. Well, 7 times, 1/4 of an amp is somewhere in the region of 1 3/4 watts. So that's quite a lot of power, and you can see this in that if you flip it over, it's got this sort of copper heatsink on to try and help it, but it still runs rather hot. So although an LDO gives us our lowest noise solution, we don't really want to use it because it's running rather warm. So the alternative to the LDO is a switching regulator. And what these look like internally is a little more than a switch. So we've got our 12 volts here, and what we do externally is we put a series inductor and a decoupling capacitor. And the way these work is that this switch turns on and off, and in neither of these states does it consume much power. So when the switch is closed, we've got a lot of current flowing through it, but the voltage across here is roughly equal to 0, because this switch hopefully has very low resistance. So when the switch is closed, we don't dissipate much power. When the switch is open, well, in that case, the voltage across it is roughly equal to V in, but the current flowing through it is equal to 0. So in neither of these states is this switch dissipating power. And that's good news because, power lost as heat is wasted and ruins our efficiency. So the voltage we get on this node here is going to look like some sort of chopped up version. So this is time on this axis and this is volts, and you can see it's switching between about V in and about 0 volts. And the reason it's 0 volts when the switch is open is actually there is a diode in here, or sometimes another FET. This isn't going to be a deep dive on DC-DCs, but the reason is it's needed so that the current flowing through, this inductor needs some sort of return path when the switch is closed, and it flows back through that diode. What this LC filter on the output does is it's effectively a low-pass filter, and it's averaging out this waveform. So hopefully by the time we get to this node, our sort of V in over time is nice and flat, because the sort of average of this is going to be a DC value if it is on for a certain time and off for a certain time. Now in reality, some of the switching noise will still get through. You know, we want this switch has to turn on and off as fast as possible. You know, while the switch is on, we said it's no power. When it's off, it said it's no power. However, this switch isn't a real physical switch, it's a semiconductor, and it takes time to turn on. And while it is turning on, it has both current flowing through it and voltage across it. So at that point, it dissipates power. So we want to turn it on as fast as possible. And this has some implications for EMC that we'll see in a bit. But because of this fast turn on, what we tend to get is on our output waveform, we actually get sort of little sort of jitters every time it switches. But, you know, with decent design, you can get this, you know, in the region of sort of 20 millivolts peak to peak. So that's what our output looks like. Now, one thing that's important to remember with switches when it comes to layout is that because we're trying to do this fast turn on and off, there are some very high current paths involved. And I now need to draw in our input capacitor. And these paths are, well, there's one I've already drawn, which is around here. And there is another one which is between the input cap and sort of the output cap. So those two paths can have very fast transient currents in as this switch turns on and off. And we need to make sure that these are laid out as tight as possible, because if you have a fast changing current into some, you know, big loop, well, that's a loop antenna and will radiate like crazy. So when we lay this out, we want the physical layout of these two loops to be as small as possible. And this is where I actually slightly disagree with how analog devices recommend you use this part. I mean, particularly see out here, you've got the outputs, the inductor and that capacitor, and it's going all over the place, you know. You'd be much better off if this Cout was placed either next to this inductor, coming back to this chip, or maybe sort of sideways, and then coming back to the chip. The other thing that I like to do is I don't like relying on the ground plane in the board. The reason is that, you know, this ground plane is shared with all sorts of other signals, and if we suddenly couple fast switching currents onto it, well, those could interfere with other circuits. So if we have a look how I've laid it out, the two key differences is that my output inductor and capacitor form this much tighter loop, so much smaller area and less likely to radiate. And the other thing I've done is I've only got vias under the actual IC itself. Now looking at this, I possibly could have done with two more, just to get the inductance down. But the key thing here is these sort of the two high current loops, actually all the ground currents get resolved in this polygon here, so that by the time it actually makes it onto layer 2, which is my ground plane, all those currents should have resolved themselves, and we should only see much lower frequency noise, sort of which is the net in from the supply. So now we've covered layout, a quick look at the schematic, but there's nothing particularly special. We've got our V in here, our enable pin, and this part has a precision enable pin, and all that means is it turns on at a very defined value. It turns on when there's 1.05 volts at this pin. I've left myself a little note here. So what I've done is I've got a potential divider such that when I have 10.6 volts on V in, that's the point I have 1.05 volts here, and that's exactly when it turns on. So I can define very carefully when this switcher turns on to ensure that my supplies had time to come up. The sync pin allowed us to use this chip in a variety of different modes, and I generally like, if I'm not space constrained, to give myself sort of resistor options to put it into any of these modes, because sometimes they have consequences that you can't always see at the time you're designing it. Int VCC is just some sort of internal logic rail that's generated, and it just asks for a decoupling capacitor. Soft start, so this is the solution to the problem we solved last week where a rail comes up too quickly and ceramic capacitors ring. So what this does is it actually gradually ramps the output voltage up over time. So by putting a bigger capacitor there, you can slow down how quickly this rises. And this part is quite nice, and it allows us to set our switching frequency with a resistor. So we can actually pick it so that our EMC, where it will appear at all the odd harmonics of our switching frequency, we can put that somewhere that hopefully where those tones don't line up with a frequency our receiver's working at. Coming over to here is that sort of output switching node. So this node we saw had very fast changing voltage, so high dVdt, so changing voltage with respect to time, and those radiate in the same way that our loops radiate over a sort of large loop area with current flowing around it. These will radiate over the amount of copper that's actually on the net. So you can see here, I've kept this node as small as possible. You know, to go from this pin to this inductor, there's as little copper on it as possible while still being able to keep the current, because otherwise that'll radiate too. Pins here that are connected how the datasheet advises, and they have this feedback pin. And what the controller will do is it'll vary the amount of on and off that it will turn on the switch inside, and what it's trying to do is keep this feedback pin at some defined voltage. Now this is from the datasheet. On this particular part it's 0.778 volts. So what I've done is I've put a potential divider such that when the output is the voltage I want, in this case 5.24 volts, then I shall have 0.778 volts here. So that'll be the point it regulates at, and a small feed-forward capacitor, so this just improves frequency response a little bit as recommended by the datasheet. So having a quick look at the layout, we've mostly gone over this. The other thing to note here is that I've kept the input capacitor as close to the chip as possible. So although I have this sort of enable potential divider here that's feeding this pin, I've decided to push that slightly further out and keep my decoupling cap as close to the part as possible. The reason for this is when this takes these sort of big gulps of current, any inductance in the trace between the capacitor and it will cause the voltage here to dip, and that'll cause the part to get upset. You know, it makes it difficult for the control loops. So capacitor as close as possible. Switching regulator gives us better efficiency, but at the expense of having that sort of switching noise on the output, which can go very high in frequency. You know, we're turning on and off that switch, so we have all the odd harmonics of our switching frequency that can go up to many sort of hundreds of times our fundamental switcher and can cause us all sorts of problems. Generally, people have gone for this approach and used sort of large LDOs and just accepted the heat dissipation. However, modern switchers have got much better in terms of their output noise, and what we can actually do is we can get the best of both worlds. We can use our switching regulator to turn our 12 volts to a voltage that is just above the rail we want. So say we got 12 volts, let's drop it down to 6 using a switching regulator, nice and efficient. What we can then do is we can use a much smaller LDO to linearly regulate our voltage down to the 5 volts we actually need. And this gives us the best of both worlds at the expense of needing more space on our board. So, just to summarise the difference between the two quickly, so for our linear regulator, or LDO, we have our input current equals our output current, and we vary that resistor to drop the voltage across it. On our switching regulator, our input power roughly equals our output power because we're dissipating as little as possible in the switch. On a linear regulator, the output tends to be low noise because, you know, we're not really doing anything to create noise on either of the input or the output, and a switching regulator will have switching noise at the frequency it's switching at and all its odd harmonics, and due to imperfections in the circuit, likely all its even ones too. A linear regulator is fairly forgiving in layout. You know, you need to put the input and output capacitor close, but not too close. It's not the end of the world, and you can get away with, you know, quite a wide range of capacitors as long as you meet the minimum. Switching regulators can be difficult to lay out well because we have those high current loops. We need to just be careful and try to lay those out as tight and compact as possible. However, linear regulators are inefficient. You know, they are doing regulation by dissipating the excess power as heat, and those can really limit what kind of situations you can use them in, whereas switching regulators are, you know, very forgiving on that aspect, and for most circumstances, apart from those with really low output current, you can generally get 80 to 90% efficient quite easily. However, because of the hybrid approach I suggest gives the best of both worlds, and I'm not really space constrained on this board, I've decided that I'm going to go for a switching regulator, regulating down to as close above the 5 volt rail that I need as possible, in this case 5.25 volts, and then I'm going to use an LDO to take the last quarter of a volt off to give me our 5 volt rail. Okay, so now we've decided we're going to use a switching pre-regulator followed by an LDO. Let's have a look at how I've actually implemented this. Now the first part I'm going to look at is our 5 volt LDO, so that takes our 5.2-ish volts out of our switcher and regulates it down to 5 volts. And the main reason to do this is to get rid of all the switching noise that could be present on this rail and give it an extra level of filtering before it goes to our RF circuits. So having a look what I've done here, the first thing I've done is I've put this 0.1 inch header with a 0 ohm resistor across it. And the reason I've done this is sometimes when you're debugging or testing your circuits, it's really useful to be able to disconnect them from the rest of what they're powering. Either I can take this resistor out and directly measure the current through these pins, or I can take this resistor out and feed the voltage in. You know, say my switching regulator doesn't work, I can manually feed in 5 volts from an external power supply, and the same on the output. And the other thing that this is sometimes quite nice for is if you're doing some really high power stuff, which are powering some really expensive chips, then you probably want to disconnect the really expensive chips until you're really certain your voltage regulator works. So I tend to do this as standard practice if I'm not space constrained. I've then got a input LC filter just to give me sort of cutoff of 16 kilohertz, so attempting to remove that sort of 2 megahertz switching noise. Here is our LDO. So input is fairly obvious. The enable pin, so this allows the LDO to be turned on and off. LED, useful on the rail, so this just allows me to see whether the rail comes on. So let's have a look at the LDO itself. Now there's not a great deal to discuss when it comes to choosing an LDO, but there's a few things that are worth keeping an eye on. Now one of the first things is called dropout voltage. Now I said these behave like a variable resistor that's to dissipate the voltage between the in and out. However, they can't go down to zero because they're actually implementing it with semiconductors. So there is a minimum voltage that this has to be higher than the output, and we call that the dropout voltage. So if we look at the datasheet for this part, you can see in the chip scale package, so really small, for Vout nominal equals 5 volts, there is a maximum dropout voltage of 190 millivolts. Now I've got it in the SOT23 package, but for some reason there isn't Vout nominal equals 5 volts, despite that being a standard part. But sort of comparing these two a bit, it looks like it's somewhere in the region of 40 millivolts higher on the SOT23 part. So let's call that sort of 230 millivolts-ish. And we've got 260, so we're all good there. The other important thing to look at on LDOs is the output capacitor. Well, sometimes the input capacitor, but the output capacitor tends to be the more important one. And you can see here it tells us that it requires an output capacitor. Recommended value is 1 microfarad, and it recommends that they are X7R or X5R. Well, what does that mean? So the dielectric material in the capacitor actually has, properties that change over temperature. So if we look here, you can see that the first letter tells you the lowest temperature it's capable of operating at, upper temperature, and then the amount of capacitance it can change over that range. Now, the datasheet recommended X5R or X7R, so we can see that's minus 55 to plus 85 or plus 125, and about plus minus 15% change over that temperature range. Now, I would generally recommend that for sort of bulk ceramics, you don't go anything worse than X5R. If you look on sorting by price on some of the websites, you can find some truly horrible stuff. Y5V is fairly common, but you can see that can have a capacitance change of plus 22 but minus 82%. And remember that this is before you've even accounted for change due to DC bias or frequency or anything like that. So they're really just not predictable. So yeah, X5R for standard and X7R if you need that high temperature, but I tend to find I rarely do. You can get other classes of this, so a lot of RF stuff is C0G, and you can see this has a temperature coefficient nominally of 0, so they don't change at all with temperature. However, this class 1 capacitors have very poor volumetric capacitance, the amount of capacitance you can fit in some space. So if you're wanting sort of tens of microfarads, you won't find it in C0G. But for RF sort of couple of picofarads in a package, this is easily achievable, and most parts will tend to be that. Going back to ceramics, X5R is good, X7R for high temperature. If you see Y or Z or a last letter that's higher than R, just run away. It's not going to be predictable at all. And one nice thing they do actually here is they tell us that the minimum effective capacitance, so that's accounting for the temperature and the effect on DC bias that we saw last time, has to be greater than 0.7 microfarads. Now, if we go back here, because I'm wanting to be sort of fairly heavily attenuating this, I've got 22 microfarads, so I've got more than enough headroom there. Now, the reason that we want this LDO is to reject the switching noise, which is likely to be at the switching frequency of the regulator at 2 megahertz. So, if we have a look, this is this parameter, which is called PSRR, or Power Supply Rejection Ratio. And that is if there is AC noise on the input of the LDO, how much of it makes it to the output. Now, PSRR tends to sort of be optimized for in the region of 1 to 100 kilohertz. And the reason for that is that above that, you can remove it fairly easily with capacitors. But you can see, looking at this bottom trace here, so I out equals 450, you know, at the 2 megahertz we've got, it's still giving us 30 dB of rejection, which is absolutely worth having. And then the rest can be removed with our filters. Now, other than the obvious, will the LDO give our output current, there's only one thing we need to look out for, and that comes back to the way that LDOs fundamentally work. Now, we said that the input current is equal to the output current, and they behave as a variable resistor, sort of dropping the voltage difference between the input and the output, which means that they can run quite hot because they're actively dissipating power. And the parameter we care about is called its junction to ambient thermal resistance. So thermal resistance is kind of how much hotter is the junction of the part going to get relative to ambient, and you can see it's in degrees C per watt, so it's a temperature rise above what, you know, the ambient temperature of the room is. So as an example, if we take here, you know, for 1 ounce copper, which is fairly standard PCB, let's take the worst case, so it's a really small board, because yeah, obviously the bigger the board, the more copper there is to dump the heat in and spread it out, and then sort of dissipate it into the ambient. You can see that we're getting round about 130 degrees C per watt. So the power that is going to be dissipated is the 0.6 amps that I've said is go through it, times the voltage across it, 0.26, because we've got 5.26 coming out our switcher and 5 volts out our regulator, times 130 Kelvin per watt. Kelvin and degrees C are the same, just with different reference points, but it's much easier to type in a K than find the degree symbol on my keyboard. And you can see when we run that, we get a temperature rise above ambient of 21 Kelvin, which is the same as 21 Celsius. So the LDO, when this thing's running full tilt, is going to be 20 degrees above ambient, or somewhere in the region of, you know, 45-ish on the desk, which is absolutely fine. You know, it'll be warm, but that's nowhere near causing any danger or causing any risk of burning, so that's all good. Now we've done that, let's go have a look at the 3v3 regulator. Absolutely nothing special here. You know, 2 1 microfarad capacitors, and the part, you know, this is just generating a nominal 3v3 for a couple of bits of switching, so I didn't put that much thought in, and the only reason I chose this was I happen to have a reel of them. You know, I'm much less bothered about stuff like power supply rejection ratio and dropout voltage on this. You know, on the last part, the dropout voltage was important because I'm passing a lot of current through it. So to minimise the power dissipated in it, so that's this bit here, you know, I can't do anything about the 0.6 amps. I need that to deliver to my circuit. So I tried to make this voltage drop across it as small as possible to limit the power. Whereas this 3v3 rail is only consuming sort of 10 microamps or something. So I don't really care about the power dissipation. I'm reckoning that the 5 volt rail should be clean because, you know, we've already cleaned this up here enough for our circuit, so I'm not bothered about power supply rejection ratio. And we've got an awful lot of volts across it, you know, 1.7 volts, which is absolutely loads for a modern LDO. But like some of the older parts you do have to watch out for, the sort of classic 7805, I think those have somewhere in the region of 2 to 3 volts dropout, so you do have to watch out for that. But yeah, that's all the LDOs covered. Okay, let's get this show on the road. So what we have here is this is the fully built up version with our capacitor that we added last time, and I've got 2 probes on the board. This right hand one is measuring the voltage on the 5.2 volt output of our switcher, and you can see that here at the bottom of the screen, and on the left we have the output of the power supply. So let's turn it on and see what happens. So good news, we've got our LEDs to come on, and we're seeing about 5.26 volts. I think we calculated that it should be around 5.24, so that sounds rather good. And drawing about 7 milliamps, that's not unreasonable for quiescent current of a switcher. However, I've also got this probe which is on the output capacitor of the switcher, and I'm expecting to see relatively quiet with bursts at our switching frequency, so about 2 megahertz. However, if we go over to the oscilloscope, we can see not all is right with the world. So, if we single capture this, so you can see there's kind of 2 waveforms going on. There's a triangular slow one, and on the rising edge there's a fast bursting one. So let's have a look at this in a bit more detail. If I use my cursors to measure the frequency of the slow waveform, you can see it's somewhere in the region of 3 and a bit kilohertz. Okay. That's suspiciously slow for a switcher. It won't be switching that slowly. But let's have a look at this. So what I've done is at the bottom is a zoomed in version of the waveform at the top, so you can sort of see the two narrow bars in the middle. That's the bit we're looking at zoomed in, and you can see this has periodic noise, and this looks much more like a switching waveform. So let's bring the cursors in here, and we've got one there, and we've got one there. Okay, so the spacing between these, it's saying about 2.2 megahertz, so that's definitely our switcher. But we need to have a quick work out what's going on with that 3 kilohertz. One last thing I want to try, let's just try zooming in on what's going on here. And if we can trigger on our actual switching signal rather than our noise, and run that continually. Oh, now that's rather interesting. So you can see sort of in the middle of this, that our switching waveforms are all aligning on top of each other. So we're triggering at some random point, and close to it, all the sort of the switching waveform 1 over is very close, and as you get further away, they're sort of smearing out more and more and more. So that almost looks like the frequency of the switcher is changing. Now, I remember this part saying it had spread spectrum modulation capabilities, so could change its switching frequency, and you do this to lower EMI. So I'm wondering if I have this thing set in spread spectrum, and that's where the 3 kilohertz is coming from. Let's just go back to this, and let's try something a little bit bold/stupid. And what we have here is I've got my precision shorting tools, and what I'm going to do is I'm going to short the 0.1 inch jumper, so I also bring up the 5 volt rail. And there we go. And that has got rid of all of our 3 kilohertz noise, so that just looks to be 2 megahertz switching noise. If we zoom in a bit more, yeah, and you can much more distinctly see here this sort of spreading out. So the time difference between the center pulse, which is the one we're triggering on, and the one next to it seems to be changing. So I think we've got spread spectrum turned on. So let's go to the datasheet and have a look at that. Okay, I think I've got to the bottom of this. So what happened is, as I built this, I had R6 fitted and R7 wasn't. And this meant that this sync pin was tied to int VCC. If we have a look in the datasheet, we can see that if it is tied to int VCC, we get pulse skipping mode with spread spectrum modulation. Now that's quite a lot of words, so let's have a look at that in a bit of detail. Starting with pulse skipping as possibly the simpler one. Basically what that is when the voltage gets, higher than the set point, that it will not necessarily turn the FET on every cycle, and you can see that here. So you can see where it's switching and the voltage is going up, and then it's getting to a point and it's going, no, I can stop switching for a bit, and it doesn't switch for a while until the voltage dips to a point that it feels the need to turn back on. And this spread spectrum modulation will, if we do a bit more looking, we can see that the switching frequency is modulated by a 3 kilohertz triangular wave, so that's where our 3 kilohertz is coming from. But I think we should possibly have a quick look at what spread spectrum modulation actually is. This is if we look at our radiated emissions, so we've got frequency here, and some sort of arbitrary amplitude here, is that we will see strong emissions at the switching frequency. But because we have that square wave at the switching frequency, we'll also have significant components at all the odd harmonics, so 3F, 5F, and these won't decay very much, and you can, if in a badly designed one, you can see emissions well up to sort of hundreds times your switching frequency if you're not careful. Now what spread spectrum aims to do is often your test limit for emissions is some sort of, some flat line or some shape. So say this is your limit, this is our limit. You get no benefit for how much you're under it in other places. All that matters is the number of points that go over. So it's no advantage if your noise floor is, say, down here, or, all the way up here. It still matters the number of points that cross it. So what spread spectrum does is it wobbles the switching frequency around a little bit, in our case by this sort of 3 kilohertz triangular wave. And what that'll give you is that instead of having this big spike at this frequency, you'll sort of get a lump. And then at 3F, because it's 3 times that, you'll get a lump that's sort of 3 times wider. Apologies for not for scale. And at 5F, you'll get a hump that's 5 times wider than that. At 101F, you get a lump that's significantly wider, because that modulation will be multiplied by 101 as well. So it'll look like sort of plus minus, if we're doing plus minus 3 kilohertz here, it'll sort of be plus minus 15 kilohertz here. And this actually has reduced our peaks of our power, and in this hypothetical example below the limit, despite the fact that you might have the same contained energy in sort of all these sections as you did in all the spikes before. But this means we pass our limit. However, for amateur radio stuff, we actually tend to not prefer spread spectrum modulation. The problem is if it's not at a well-defined frequency, it just sort of becomes broadband noise everywhere that's very hard to do anything about. Whereas if we have these well-defined spikes and then a noise floor that's very low everywhere else, well, we can make sure that, you know, with a bit of planning, we can put our receiver band, say, so it's here, between these two, and then we won't have any tones present and it'll be nice and quiet. You know, it's much easier to deal with the enemy you know rather than just it being everywhere. And if we spot something and you go, ah, that is an exact multiple of the switching frequency, well then you know what it is and you can do something about it. So I think we've got to the bottom of all of that, and I think the answer is we just need to change that sync resistor. Okay, so I've gone and done that mod, and I've now got two scope probes on. So the yellow one is on the output of our switching regulator, and the green one is on the output of our LDO. And if we go to the oscilloscope, these are on the same scale, but you can see that although our 5v2 rail still has noise on it, you know, it's much less well defined in terms of frequency. You know, if we bring our cursors up, you can see that now we've sort of got a frequency somewhere closer to sort of 8 kilohertz, but that's not entirely consistent. But our 5v0 rail is completely clean. I mean, for reference, this is running right now, and if I unplug the 5v0 probe, you can see that did nothing to the amplitude. So we're looking at the self-noise of the scope, so I'm struggling to actually measure this, but it's giving a good rejection of what's coming out of our switcher. You can see if I put that in its lowest mode, that's entirely self-noise. So that looks rather good. Okay, so I've gone ahead and put a 7.5 ohm load resistor on it, so this should easily take it to beyond the 600 milliamps it's spec'd for. Now this resistor is not appropriately sized for the whole thing. Its power handling is only about half a watt, and we're expecting, you know, somewhere in the region of 2 watts to be dumped into it. So I'm not expecting this experiment to last very long, hence the thermal camera. But I just wanted to show you that noise of a regulator changes with load. So if we have a look at the scope, what we have here in sort of orange is the output ripple under no load conditions, or just that of the 5-volt regulator, so a couple of milliamps. So let's turn the power supply on and see what happens. And let's turn that on. First of all, you can see how much the noise is so much larger than before, and whoops, that resistor is getting really quite hot. So let's turn that off because you can see it smoking there. Okay, so just having a look back at the results there, now my bench is no longer smoking, we can see that the output voltage ripple got an awful lot higher. Now I've spent quite a lot of time for this part actually trying to find the output voltage ripple specs. However, I can't actually find any that aren't for under very light load conditions in burst mode. However, even here we've got sort of 150 millivolts peak to peak, and by the time that's gone through our LC filter and our supply with PSRR of, you know, somewhere in the region of 30 dB, you know, this is going to be a lot smaller, on the order of microvolts, and will be easily filtered by local filtering, because we do have ferrite beads and local decoupling caps on all the parts. But I'll keep an eye on it and see if it's a problem. You can certainly get parts that are specified for lower ripple than that, so it might be a reason to switch to a slightly more expensive part. So I think that's about it for today, so just sort of wrapping up quickly. So for modern electronics, even if you were told, you know, LDOs are the only way to go for RF circuits, we can absolutely do a lot better job in terms of efficiency by using a switching regulator as a pre-regulator, and then using an LDO with a small dropout voltage. When laying out your DC-DC, make sure your tight layouts between your sort of input cap, your switching elements, and your output cap is all very carefully considered. Remember that capacitive materials have different properties and how they change with temperature, and stick to X5R or X7R caps for predictable behaviour. And when you're picking your LDO, you should be looking at your input and output capacitor requirements, the dropout voltage, be calculating the power you're going to be dissipating in it, and ultimately your thermal resistance, because that's what determines how hot it's going to get. And if you're using it in this application, look at its power supply rejection ratio, because some of them can be very poor, above a few tens of kilohertz, and we tend to be switching at much higher frequencies nowadays. Anyway, that's all I've got for you today. Thanks very much for joining me, and 7-3.